Coming to us from sunny Florida is Mr. Greg Shanos. Greg was a member of Skyscrapers back in the late 1980s. And I remember him very well. He since moved to Florida and left us and rejoined us with the COVID outbreak a couple of years ago. I remember Greg as a young observer and a pharmacist, and he has a degree in pharmacy and chemistry, also a Master of Arts in teaching, and he's retired to Florida, and he's going to give us a talk tonight on OSIRIS-REx. So, Greg, you can continue with your description of what you're going to talk about. I will let you go.
All right, great.
Thank you.
All right, thank you, Linda, for that introduction. First, before I start, I'd like to dedicate this lecture to my friend Dave Eustace, who recently passed away. Dave is the reason I became an amateur astronomer. I read in the fall of 1985, he had written a article in the Providence Journal entitled "Comet Halley Coming at You." And I read the article. I said, "Oh, wow, Comet Halley's coming. I have to see this." So there was a number to call. I called it, and there was an answering machine. I left a message on the answering machine and a callback number. And I didn't hear back till about 2 weeks. Then Dave called me, and he said he was on his honeymoon. I was the first number on his call list. And so he told me about Skyscrapers, and I attended. And when I first entered the ante room, I remember there were two ladies, and I asked for Dave Eustace, and one of them said rather defensively, "What do you want with Dave?" And I explained to her, and she said, "Oh, I'm Tina. I'm his wife. I'll take you to him." And the other lady was Kathy Syak. And so very fond memories. The Eustaces were invited to my wedding, so were the Syaks, and Bill Gusler was a photographer. So good times, and he was a great friend and a good person. So, all right. To a happier note, let's begin the lecture. Can you all see my presentation there?
Yes.
Yes.
Okay, great. Okay, so there was a mission from NASA called OSIRIS-REx, and Hayabusa 2 was from JAXA, which is the Japanese version of NASA, and it went to two asteroids. OSIRIS-REx, NASA went to Bennu, and Hayabusa 2 went to Ryugu. So and they returned actual samples of these asteroids. So I'm gonna discuss this tonight. So OSIRIS-REx is actually an acronym, stands for Origin, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. That's a mouthful. Right, you don't have the side slides.
Yeah, that's correct.
All right, great. Okay, so like I said, OSIRIS-REx stands for all this. Okay, can you see that animation? Okay.
Yep.
Oh, fantastic. Okay, so Asteroid Bennu. This is the original radar that was taken, and from this you can see the complete rotation, and this is the shape model of it. It's basically 5 football fields or 0.3 miles. Okay, and it has like a spinning top kind of appearance, and it's 4.3 hour period, rotates once every 4.3 hours, and it's a near Earth asteroid, so it's not confined in the asteroid belt. It actually crosses the Earth, see, as you can see here. Okay, so why was Bennu chosen? Out of greater than 500,000 asteroids whose orbits are known, 7,000 of those are near-Earth asteroids. Oh, can you see my pointer? Can you see the?
Yes.
Oh, good. And then 192 have optimal orbit for sample return, and then 26 had a diameter greater than 200. 5 were carbon rich, and so Bennu was chosen out of all of them. Okay, and then Osiris, the mythology. Osiris was the Egyptian god emperor and son of the sky and the earth. This is Osiris. He's basically Zeus to the Greeks and Jupiter to the Romans. Okay, so that was oh, there it is. Okay, and then so Bennu was not the original name. The original name was Asteroid 101955 1999 RQ36. This would be a great password if you could remember it. This was the official designation, and the Planetary Society wanted a much easier name than this to call it. And so a 9-year-old kid, Mike Puzio, named it Bennu. And what impresses me is a 9-year-old kid would know Egyptian mythology this well. And so Bennu is the Egyptian mythological bird that was born from the heart of Osiris. And notice when you look, and it's basically a great blue heron. And if you look at it, the spacecraft, doesn't it kind of look like a bird? Here's the solar panels, and then here's the beak, which is the high gain antenna, and then here's the touch and go sampler. And this is kind of one of its legs, if it's standing on one leg like a flamingo would. So isn't that kind of cool? It does look kind of bird-like. So, and then the mission timeline here, the big thing, the launch in 2016, it arrived 2018. It actually collected the sample on October 20, 2020, and then returned to Earth September 24, 2023, and then funding. Can you mute? All right, thanks. So here's basically the spacecraft. This is all the instrumentation on it, the solar panels, the high gain. This is where the sample return capsule was, and then this is the touch and go sample collecting mechanism. And then this is what actually collected this. And we'll talk more about that later. So, surprise, Bennu is very rocky. Scientists expected Bennu to actually be like a sandy beach, very fine grained. And the reason for that is because it had low thermal inertia, which means a small particle size. So think of when you're on a beach and you're walking barefoot, right? And it's a sunny day. Your feet feel very hot because the sand is hot. It heats up quickly. And then once the sun sets, the sand will cool down very quickly too. Okay, that's because of a low thermal inertia. And that's what the instruments on Earth detected for asteroid Bennu. So they thought it would be a fine sandy beach. And no, this is what it was. It was a rubble pile asteroid, had a lot of rocks, and the rocks actually were quite porous, and there was a lot of fine regolith on it. So the fine regolith and the porosity was what we were detecting as the low thermal inertia. So that's why we thought it would be fine sandy beach, and it wasn't. But there was no turning back. Okay, and look at some of the boulders. One of them is as tall as a 6-story building. So it was a real shock when the OSIRIS-REx got very close to Bennu. And here's a complete rotation of it here. And then you can see the 4 sides and the map. The craters about 100 to 1 billion years old. Note the lack of craters. And the reason for this is because think about it. If you have a solid surface and you have something impacting it, it's going to make a nice crater. But if it's very porous and very loosely held together, the energy is going to be dissipated out throughout all that porosity, and so it's not going to make such a large impact crater. Does that make any sense? You know, so the fact that it's very porous and loosely held together, you're not going to get any deep craters on it. Okay. And then significant discoveries. This article just came out. The OSIRIS-REx spacecraft, they were measuring the craters, and they detected that they infer a layer of fine-grained material that would be 1 to 4 meters thick that's directly underneath it. And the craters that were smaller in size, 25 meters or 82 feet, they appeared smoother than the rough surrounding terrain, whereas larger craters, they were just as rough as the outside. And spectra were taken of these, and the redder craters were younger. And so that was the analysis of that. And then significant discoveries. The albedo is very dark. Albedo is just a fancy term for reflectivity. So a mirror would have an albedo of theoretically 100%. All the light that hits a mirror is going to bounce back. And a dark charcoal briquette would have an albedo right around this, 4.5%. This is actually darker than a charcoal briquette or freshly paved asphalt. Okay, it's very, very dark, and the density is very low. You know, most rocks are about 3 or 4 grams per cubic centimeter. So these rocks are very, very porous, very not very dense at all. And then, so I'm going to mention these, and I have a slide on all of these. Water is present in rocks, 2.7 micrometer band detected in the spectrum. Minerals are transformed by water into phyllosilicate, clay, and magnetite. Bennu is a close match to Ci and Cm meteorites. Sun's radiation causes it to speed up 131 feet per day via the Yartarsky effect. First ever particle ejections from an asteroid. And look at this, they even discovered a black hole in outburst by one of the instruments here. It was actually in an X-ray outburst. So that's kind of cool. On November 11, 2019. Okay, so what is the Yartarsky effect? This is pretty easy to understand. The sun heats up half of the asteroid and the other half's in darkness. So as it rotates, and remember it rotates in 4.3 hours. So as it rotates, this heat gets dissipated into the dark coldness of space. And so this kind of makes a little thrust. And so through time, it moves. Okay, so that's basically the Yartarsky effect. So it's pretty easy to understand. Half of it is heated up, and as it rotates, this heat is dissipated, and it kind of makes a thrust. And since there's no friction in space, it moves at 131 feet per day. Okay, so that's the Yartarsky effect. Conformation of water, 2.7 right here, micrometers is where water is absorbed. Okay, and then this is the spectra of Bennu, and then these are the spectra of these meteorites here. This is Orgay, Murchison, and this is Allen Hills from Antarctica. So the fact that that Bennu has a lot of water is very, very significant. And then this was another surprise. Bennu contains materials from another asteroid. So remember, it's very dark, 4.5% albedo. Okay, but notice there were these really bright fragments here that really stood out. So the spacecraft took spectra of this, and they found that it's igneous pyroxene, and there's no pyroxene on this is made of carbonaceous kind of material. So this actually matched the spectra of asteroid Vesta from the Dawn mission, and I have a lecture on the Dawn mission to asteroids Vesta and Ceres. Hint, hint, if you want to hear that in the near future. So there's pieces of asteroid Vesta on Bennu. That is really cool. But Vesta is an inner belt asteroid. Remember, this is an Earth-crossing asteroid. So where did it come from? Well, two theories. The fragments came from, they impacted they think that Bennu may have been an inner belt asteroid. The parent body was shattered by impact, reassembled outside the belt, or fragments may have impacted it on its current position. So those are the two ideas. So that's kind of neat. We have pieces of asteroid Vesta on Bennu. Okay, another surprise was that Bennu is shedding its skin. This was discovered by Dr. Carl Hergenrother. He's ALPO, Association Lunar Planetary organization, and he's the Comet leader of the Comet. So I send him my images of comets. But what's interesting is he made this. To see these specks here, these look like stars. So he thought at first these were stars, and he was trying to match them with stellarium of the exact position, and nothing matched. And then he was looking at them at different times, and these moved. So the conclusion was that this is actually pieces of Bennu that are shedding. So scientists were actually able to look at individual particles here, and in this animation, find a trajectory. Isn't that cool? And from that, they're able to determine the internal density of Bennu. So that is fascinating. And then these are the proposed mechanisms for what would cause this shedding of its skin. And the red are the more favored hypotheses. So now those were all observations made by the OSIRIS-REx spacecraft orbiting. It orbited and mapped the whole asteroid for over a year. Now, once everything was mapped, it was determined where are we going to actually land. So there were 4 potential sites chosen, okay, to actually collect the sample. And since it's so rocky, look at it, and not a nice sandy beach, they had to choose the site very carefully so that it wouldn't disrupt the spacecraft. So before I do that, I just want to talk about Brian May, a rock star astrophysicist right here. He was one of the co-founders of the rock group Queen with Freddie Mercury and drummer Roger Taylor. And what's interesting is at the time he was going for his PhD in astrophysics at Imperial College of London, ranked 6th best university in the world. Okay, he co-wrote a lot of songs, had a solo career, was one of the top 10 guitarists, has a genius IQ, and check this out. As of 2024, his net worth is $260 million. And what impressed me the most, okay, is that back in 2007, he went back to Imperial College of London to finish his PhD in astrophysics, okay, that he began 30 years earlier. And this is the thesis title, A Survey of Radial Velocities in the Zodiacal Light Dust Cloud, 256 pages. Google this, it's online. I downloaded it. And he had to learn coding and computers that weren't around in the 70s, the code written in the thesis too. It's just amazing. And what impresses me is that someone with over $200 million would go back and finish his PhD thesis. I mean, that's very inspirational. So think about it. If there's anything in your life that you left behind because, life got in the way, go back and finish it. Brian May did. Okay. So I think it's very inspirational. And think of it. He has the perfect blend. The left side of the brain is science and the right side of the brain is art. And usually you're either more left-brained or right-brained. And, being into astronomy, we're all more left-brained scientific thinkers. He has the perfect blend of art and science. I mean, it's amazing. Think about that, But the reason I mention him is because NASA consulted with Brian May, and he wrote this book here, Bennu in 3D. And every single crater and stuff has been mapped out. And Brian May was instrumental in determining which landing site we're going to take. So isn't that cool? And Roger Taylor here, he was going to be a dentist. He was in dental school at the time, but he's worth about the same amount of money, but he didn't go back and finish dentistry and open up a dental practice. Okay. So it's really, dentistry is much more lucrative than astrophysics. So it's really impressive to me that someone would, do that. Okay, well, enough hero worship. Okay, back to. So these are the 4 sites that Brian May and Dante Loretta here, the primary investigator, determined would be the best place to to uh, to grab a sample. So then it was decided between Nightingale and Osprey, and the decision was Nightingale. Okay, and I would think Osprey because it looked like there's got this huge rock here, you know. But Nightingale was chosen, and the main reason was because it has the highest color variation, which suggests diverse materials. So and this is kind of a parking lot here, kind of showing that this spot is where they picked this. See, it's pretty there's a lot of rocks here, but it's pretty smooth here. So that's the site that was chosen. And then here you can see the touch and go apparatus mechanism. So it touched down and it ejected nitrogen gas, and then right away sucked up so it went underneath the regolith a little bit and then sucked up what was underneath. Okay, and they use nitrogen because it's very inert. You know, oxygen is very reactive with a reactor, so nitrogen's an inert gas, and so that's what was chosen. So they wanted to collect about 60 grams, 2 ounces of regolith, and they collected so much that a lot of it was leaking out. If you look at these little black specks here, those are parts of Bennu that are leaking out. We collected so much, and now it's putting it in the sample return vessel. So these are all the times. And then on September 24th, 2023, it returned to Earth in Utah, and then sent right away to NASA's facilities. Here's the return sample. And what was great, though, is the mission is not over. The OSIRIS-REx has been recommissioned to go to another asteroid called Apophis. And now they've renamed it OSIRIS Apex instead of OSIRIS-REx. Apex stands for Asteroid Photometry Explorer. So photometry means they're just going to image it and map it out because there's no way to collect another sample now. That's already been done. So that's really cool. And now Apophis is a ordinary chondrite type of asteroid. It's an S asteroid. Okay, this is the C or carbonaceous kind of asteroid, and this is the size of Apophis. And the scary thing about Apophis is on April 13, 2029, it will pass closer to the Earth than the geosynchronous communication satellites and will be 19,600 miles above the Earth's surface. So if you look here, Apophis is here. Look at that. These are the geosynchronous satellites. The moon is over here. It is very close. It's scary close. But NASA says it's not going to collide with us, which is a good thing. And then during the 2029 approach, its brightness will peak to magnitude plus 3.1. It'll be easily visible to the naked eye and will move at an angular diameter of 42 degrees per hour. So if you divide that by 60, that's 0.7 degrees per minute. So that's like 1.5 Earth-Moon diameters per minute. That's going to be moving pretty fast. And if you look at it through a telescope, it'll have an angular diameter of 2 arc seconds, which is the size of the angular diameter of Neptune as seen from Earth. So this should be really, really cool. And then in 2029, there'll be another thing that's going to happen. Psyche mission. There's an asteroid Psyche, which is the first metal asteroid. And there's a spacecraft headed to that, and that should arrive around August 2029. And then in October 2029, I turn 70. So that'll be my 70th birthday present. Apophis coming close and seeing what a metal asteroid looks like. So here's Apophis here. These are satellite images of it. Okay, and here's when it was brought into the OSIRIS-REx capsule. And they opened it up, NASA opened it up, and it was all presented on October 11, 2023 on YouTube. It's there. And what happened is they attempted to go inside and they couldn't because 2 out of the 35 fasteners could not be removed. They had to develop special tools. So this was the first sample return here. And this thing weighed how much did it weigh? 70.28 grams. So that's quite a bit of material that was still out there. So that's kind of cool. And then this shows the different types of the rocks. You had the finer grained and the larger material here. And then light microscopy. So the Bennu particles contain 4.7% carbon. That's a lot of carbon. That's more than the carbonaceous chondrites that we have on Earth. And then carbon forms covalent bonds with hydrogen, oxygen, nitrogen, sulfur, and phosphorus, okay, and to produce prebiotic and biological compounds. This is referred to as organic carbon, okay? So carbon bonded to basically CHON, okay? If carbon is bonded to itself, it's non-organic. That's inorganic carbon. And carbon bonded to itself is graphite, which forms hexagonal sheets, or diamond, which is tetrahedral. And now there's a third form of carbon called fullerene, C60, C70, and there's nanotubes, and it's just amazing. So now the scientists are looking for amino acids, they're looking for nucleotides, they're looking for all sorts of organic compounds in here. And then the UV light, all these glowing globules are organic carbon. Isn't that cool? Okay, so if you look here, serpentine has water locked in the crystal structure, and then this sulfide minerals are here, and sulfur is important since they form sulfur links, bridges in amino acids, and also it's an indicator in planetary evolution how quickly things melt. And then they also found magnetite, which is lodestone. So this will react with magnetic fields and get paleomagnetism. So it's really cool. And then look at this. This is a CAT scan for rocks, X-ray computed tomography. This is so cool. Without cutting the rock, you can do a CAT scan on it. And the red are sulfide minerals. So if you're going to cut this rock, you know where to cut it. You don't want to cut it here because this part doesn't have much sulfide. You want to cut it more here. See? So now you know exactly where in the rock you want to cut. So that's cool. Okay, and then success. NASA finally opened the lid off Bennu's asteroid capsule. So here's the outside again with the original 70.28 grams. Here's some of the special tools they developed to open it. Okay, and they use a lot of dental kind of tools. And then finally on September 24th, 2023, it took 3.5 months to fully open. And here's what it looked like when they removed this top lid. Look at it. Look at all that. So now they're guessing how much. They had to accurately weigh it. So that took a little more time. So they're thinking it's between 120 to 250 grams. And the total is 121.6 grams. And they isolated it here based on size. See, these are the larger ones, and then these are the finer grain. So isn't that cool? And they're going to preserve 70% of it for future generations. And then more than 200 researchers around the world are working on this. So that's really cool. So we got 121.6 grams. A spoiler alert, when we went to Ryugu, only 5.4 grams. That's it. And here we got 121.6. So this was a very successful mission. The other one was too, but we didn't get as much. But you don't need much to do a lot of the scientific research. You just need milligrams of the stuff. So here, scientists have broken down the 3 different types: this hummocky, angular, and malted. And then this is the characteristics of it. You can read a lot of this for yourself, but the big thing is the Hamakati morphologies have the lowest densities, and the malted have the highest densities. And then what's important here is that they found a lot of clay minerals that are similar to Earth's mid-ocean ridges. So this implies that Bennu had a watery past, okay? And they did a lot more. See, notice how this has a lot more whiter stuff here than here. So there's a lot of difference in morphology in these specimens. Okay, the phosphate surprise. OSIRIS-REx, the spacecraft did not detect any phosphate in the spectra, but that's why it's important to actually bring home a sample, because you can only do so much out there. Best thing is to bring back a pristine sample like we did here. So the bright patches here are basically magnesium hydrogen phosphate trihydrate. And the phosphates on Earth are found on mid-ocean ridges, and also they detected it on Saturn's moon Enceladus. And then this, so you knew there was a lot of water when you see a lot of this phosphate. And they also detected polyaromatic hydrocarbons. We'll talk more about those when we get to Ryugu. But naphthalene, does anyone know what naphthalene is or used for?
Mothballs.
Yes, mothballs, exactly. But you got to read the label carefully, because they also use dichlorobenzene for mothballs too. So read it carefully. It's dichlorobenzene or naphthalene. But yep, they're mothballs. And then pre-solar silicon carbide. These were formed from a nearby supernova and ejected into our solar system. And they're commonly found in carbonaceous chondrites. This is really cool. So they've been identified too. And then also nanodiamonds have been identified in the Bennu samples. So there's a lot of cool stuff here. And then this just came out recently. They found the salty brine. Pockets of liquid water may float underneath Bennu parent body. Cracks and fissures allowed the water to evaporate to the surface, leaving behind the salty brine. And it was determined to be sodium carbonate, which is confirmed. So all these crystals that you see here are all sodium carbonate. Baking soda, sodium bicarbonate, NaHCO3. Okay. And then, ta-da, amino acids are present in the Bennu samples. Okay, so this is what scientists have really been looking for. So let's go over some of this here. So this is what an amino acid is. Okay, it has a central carbon. And the reason it's called amino acids is because they have an amino group, which is a weak base, and then a carboxylic group, which is a weak acid. And then it has a hydrogen here, and the R group is what defines the amino acid. If you put an H, a CH3, a CH2, a benzene ring, that defines the individual amino acid. Okay, so that's why it's called amino acid, amine group and an acid group here. Okay, and then and then another important thing about amino acids is they have something called chirality, which means handedness, left and right. So the left-handed isomer is called left, and then the right one is called D and L, and they're not superimposable. You can't, put a right glove on a left hand, okay? But if you turn it 180 degrees, your hands can go like that, see? So they come in D and L forms, okay? And Bennu had an equal amount of D and L, and that's good because life only uses the L amino acids, okay? If you were to consume D amino acids, you'd starve to death. Your body couldn't use them to form proteins. It has to be the L, and all living organisms have the L. Okay, so that's really cool. So researchers found 14 of the 20 amino acids used in biology to to build proteins. Isn't that cool? 14 out of 20. And then there were 19 non-protein amino acids that are non-existent in biological organisms. I'll give some examples of that when we talk about Ryugu. But this is really incredible. And then I love this slide. These are the 14 amino acids that are that we use to form proteins that are found in Bennu. And you can see here, this here has a carbon. They don't show it because it gets very messy. But here's COOH, CH3, that's alanine, and then the H would come up here. They don't show that just to clean it up. But if you know chemistry, it's understood. Okay, so those are the proteogen. And then building blocks of DNA and RNA were found. This is really amazing too. So these come in two varieties, pyrimidines and purines. So so thymine, cytosine, and uracil are pyrimidines, and purines are adenine and guanine. Uracil is found only in RNA. These are found in DNA. Okay, but uracil is only found in RNA, not DNA. But this is really cool. But the concentrations of these are much lower in the Bennu samples as opposed to meteorites like Orgay and Murchison that contain much higher amount. And then they also found xanthine, hypoxanthine, nicotinic, vitamin B was also detected. Isn't that cool? Vitamin B3 in the Bennu samples. So to summarize everything, I love this slide. This just came out a few days ago. So precursor molecules, all you need, and this is what was used in actually the Urey Miller synthesis back in the 50s. Water, formaldehyde, and ammonia, and you just need a heat source and some electricity, and you'll form amino acids and a lot of other organic compounds. And then you need a substrate or a catalyst to get this going. So you have these minerals here, magnesium, sodium phosphate, sodium chloride, clays, and then this trona here is just a sodium carbonate and sodium bicarbonate together. All right, and then this is saponite, which is this clay, this complicated chemical structure here. And then you have the purines and pyrimidines, which form the nuclear bases of DNA and RNA. And then you have the amino acids, which have the D and L isomers, okay? So this kind of puts it all together, the organic stuff that was found. And this is the open part. So ingredients, environment, and organic compounds. All right, so let's stop here. Any questions on Asteroid Bennu before we go on the Hayabusa mission? No questions? Okay, speak now or forever hold your peace. Where did I hear that before? But okay, so the Hayabusa spacecraft. Now, this is Hayabusa 2, which implies there was a Hayabusa 1. So the original Hayabusa went to an S-type or stony asteroid called Ikuta, which is, and here's, it imaged it, and it tried to collect a sample, but it only got 1 milligram or 2,000 particles. So that wasn't very successful. But it confirmed that it had water, organic matter, and amino acids in this asteroid too. So that was kind of cool. But and they confirmed the link between ordinary chondrites and the S type of asteroids. Okay, so that was the original. This was back in 2005 and returned to Earth 2010. Now Hayabusa 2, Hayabusa means falcon. Okay, so this is from JAXA, and here's the timeline for this. It launched 2014, arrived 2018, sample collection 2019, returned later that year, and then arrived on Earth December 5th, 2020. So this actually came first, Hayabusa 2, okay, and then OSIRIS-REx. And then here's here's the payload here. Same basic idea. Had the sample return. This is what collected, and then but this had something extra. Had rovers that actually landed on the asteroid and transmitted data back, which is really, really cool. And then here, here's some basic facts on asteroid Ryugu. It's a carbonaceous asteroid again. Notice how similar it looks to Bennu, huh? It still has that spinning top appearance. Looks very, very similar. And this one, though, is 0.56 miles. Remember, Bennu was 3.1. So it's almost double the size of Bennu. And Bennu took 3 hours. This takes 4 hours. This takes 7.6. So about double the time to rotate, one complete rotation. And then the spectra is pretty uniform on large scales, heterogeneity on smaller scales, top 1 meter layers less than 1 million years old. Great variation in both. Brecciation is when you get rocks that are smashed together and melt together, so you have different types in there. And then this was significant. Ryugu exhibits a lower water content than Bennu, and this may be due to heating, impact melting, or aqueous alteration. So there's less water on Ryugu than Bennu, but there still is water there. And then here's the mascot, the Mobile Asteroid Surface Scout, that actually landed on the asteroid. So this is the iconic photo from that. That was really cool. And you can read a lot of this for yourself, but this is when everything was collected, the timelines and everything. And then it returned to Earth on December 5th, 2020, and landed in Woomera district of Southern Australia. And my wife and I have been to Woomera in Australia. It's out in the middle of nowhere. There's a military base there that we saw, but there was a total solar eclipse in December of 2002, and so we went there to see it. It's only, I remember, 30-second eclipse. It was very little, but we saw it. But it's kind of cool that I actually been to Woomera where this thing landed, and then they returned the samples to Japan right away. And here it is. Here are the samples. And notice, this is actually a microscopic image of it. This is only 1 inch, 25 millimeters, and the inside is only 21 millimeters. See? So the total is 5.424 grams. And remember, OSIRIS-REx had 121.6 grams, so that's huge difference. Okay, this is only like a little teaspoonful of material, but a teaspoonful is better than 1 milligram that the original Hayabusa had. So this was still a phenomenal success. Like I said, you don't need very much of this sample. All you need is a few milligrams of this to do research and determine amino acids and other compounds. Okay, and this was a surprise. This came out recently in 2023. Scientists have discovered that there's these rods and filaments, and they found that they were actually growing every 5.2 days. So these things were kept under nitrogen as in a supposedly sterile environment. They still got contaminated with organic matter. That's bad, because if you're trying to find organic compounds, now you don't know if the organic compounds came from the contamination or from Ryugu, so that was a surprise. Hopefully the same doesn't happen with the Bennu samples. But proposed mechanisms for formation. This is how Bennu may have formed. An icy parent body forms outside the solar system. Radioactive heating causes the ice to melt, causing minerals to modify by aqueous alteration. And impact disrupts the parent body, but does not cause widespread heating. It reaccumulates much closer. So they think it formed a lot further out past Jupiter, and then reassemble closer. And this is an Earth crossing asteroid too. This is not in the asteroid belt. It crosses the Earth. Okay, and they determined paleomagnetism. The particles contain magnetite, and so they were able to determine 3 millitesla magnetic fields. That's kind of cool. And they found nanodiamonds in it too. And another theory is that it may be an extinct comet. Think about it. If a comet were to lose all its gas, all right, it would be indistinguishable from an asteroid. So this is what these authors were saying here, that as it came in, since it comes closer to the Earth and to the sun, and then it'll, if it were a comet, it would heat up, and eventually the ice would sublimate. And then as more ice sublimates, it would spin faster and faster. Angular conservation of angular momentum, like the figure skater, you pull your arms in, you spin faster. So as the ice leaves, it would spin faster and form this top shape. And so you'd have modern day, Ryugu. So here's 2 contrasting theories: one that it formed further out and reassembled inward, and one that it may have been an extinct comet. Okay, so this is from the samples now. Water is confirmed in asteroid Ryugu. Remember, this 2.7 micrometer absorption line here, that is for water. Actually, it's hydroxyl. And remember, water can dissipate ever so slightly into H plus and OH minus, the H2O. So really you're detecting hydroxyl here, but if you have hydroxyl, you have water. Okay, so. And then Ryugu contains organic carbon, so they want to see if there was any carbon. So the 3.4 micrometer here, and on either side of it, these absorption bands here indicate that you have carbon hydrogen bonds, which is organic. Okay, and then the ones that match, the closest meteoritic on Earth that we have is this Tagish Lake meteorite, and this is from my personal collection. I took a picture of it, and this, notice this has the closest match to the Ryugu samples. So they're comparing known meteorite classes here, and this one has the closest. And then Ryugu contains amino acids. Yay, so 15 have been detected, okay? And then the non-proteogenic ones. And remember I said, I'll talk about this in a sec. So polyaromatic hydrocarbons, they found uracil again. They found vitamin B3, nicotinic acid, okay? And the 15, so these are what are known as non-protein amino acids. See, this is not used by living organisms, 3-amino-2,2-dimethylbutric acid, okay? And all of these are not used by living organisms. So, and plus they're DNL, so they're equal mixtures of 50% right-handed, 50% left-handed. Now remember, life only has left-handed. So if you see a lot of L-alanine or L-valine, those are used by living organisms, then it's probably contamination. But when you see equal amounts, like you see here, then you know it's glycine is the only one that does not have the mirror symmetry because it's another H. So you have 2 H's, so you don't have the mirror symmetry in glycine, but that's the only one. And then, so that's it for Ryugu. So they discovered amino acids, and then this one sums it all up. And this shows the chemical structures of each, which I like. So this is pretty universal. So gray or black is used for carbon, white is hydrogen, red is oxygen, and blue is nitrogen. Okay, so this is what a polyaromatic hydrocarbon is. It's just carbon and hydrogen, like it says. Aromatic means you have these benzene rings, these flat benzene six-membered rings. And so polyaromatic hydrocarbons, okay? And these are very flat molecules, and these are tar molecules. So when you drive on the road, so next time you're driving on the road, just think of this. You're driving on a carpet of polyaromatic hydrocarbons. Seriously. And this is pyrene here, okay? And then carboxylic acid. So this is CH3, C double bond OH. So this is acetic acid. And what common food product is acetic acid found in?
Vinegar.
Vinegar, yes. So if you had a salad with with vinaigrette or vinegar, yep, this is vinegar. 5% acetic acid is vinegar. Yep. And then these are amino acids here. We talked about those, but this has 2 carbons, so a little more complicated amino acid. And then here's an amine. So you have CH3, CH2, NH2 here. So this is ethylamine here. And then this is nitrogen containing heterocycles. This is a pyrimidine here. This is where you have carbon and then 1 nitrogen in this ring. Okay, and then this is the sample here, and there's Bennu. So that's kind of cool. So this is a summary of all the different classes of organic molecules that have been found in Ryugu. Okay, and notice, what did I say? Organic carbon is carbon bonded to hydrogen, oxygen, nitrogen. Okay, and that's what you see here. Okay, and that's basically it. And then look at all the things I read to put this together. So, and notice, here's Bennu and here's Ryugu. Isn't that cool? Look how similar they look. So any questions?
Anyone? Any questions?
I have just the one. Had they initially planned for the OSIRIS-REx spacecraft to be reused, or is that something they kind of figured out after it came back that it could be done?
I think they figured it out after. Yep. Yep, they figured it out after. They were probably thinking about it, but they didn't know at the time. But the way the orbit worked out, they probably thought, let's try it. And then they did the orbital calculations and they found, yep, we could do it. And they went for it. So that's cool because you get a 2-for-1, you know? Yep. Now we're going to image another asteroid. We're going to orbit it and image it, Apophis. And it's as it's coming into us. And like I said, it's going to be a 3rd magnitude star we're going to see it as. That's going to be something moving rather quickly.
Are they planning any more of these types of missions in the near future?
The one that's currently going on is Psyche, asteroid Psyche. And that one, everyone is very excited because that is a metal asteroid. You know, meteorites, you know, you have stones, irons, and stony irons, right? So every asteroid we visited so far has been, you know, a stony. Even these are stony meteorites. They tend to be richer in carbon, but they're still stone asteroids. Here, this is an iron asteroid. So it's probably from a core of a planet, and they actually found olivine on it. So it could be like a palisite type or mesosiderite. You know, it's really exciting. And how do you form you know, crater on a metal asteroid? I mean, be fascinating to see. It'll be the first of its type. Well, that'll be in August of 2029. So I'm looking forward to that. And then Apophis is coming in at that time. So we got 2 things to look forward to.
Any more questions?
Yeah, since they had that reaction of certain structures actually growing when they were in nitrogen, which is not totally inert, why don't they use something like argon, which is totally inert?
Oh, probably because expense. I mean, think about it. We tend to not think about it, but the atmosphere is basically 75% or so nitrogen, right? And 24% iron, a few percent trace gases, right? Carbon dioxide, water, trace gases. So it's mostly nitrogen. So it's easy to extract nitrogen, pure nitrogen from the air, right? And whereas argon, I don't know where they'd extract that from, but it would be much more expensive, and they probably have to keep it circulating in the in the hoods and whatever they keep it at too, not just have it there. They probably have it, circulating through. So, I think just expense. Nitrogen is used universally for a lot of these, any inert gas can be used, but nitrogen is the one that's that's considered. Yeah, you're thinking of the noble gases, argon, xenon, all that. Yeah, I think they're just much more expensive. Any other questions?
Well, I was just thinking that the nitrogen is reactive with some of the carbon compounds and structures that they found. So it would seem hazardous to use nitrogen to destroy your sample.
Yeah, I never thought of that, but that's what's used, and that's what was used to, doing the touch and go. They shot nitrogen out, the stuff came out, and then they sucked it up right away. So, yeah, that's what was used.
Anyone else?
I just wanted to say thank you. I really enjoyed your presentation. It was wonderful, and I enjoy the research you've done to put this together. I'll review it again in my own time, but I thought it was great. Thank you.
Okay, I can send you a PDF. I can send Linda a PDF, and you can send it to all the skyscrapers. It's not that big. The PowerPoint is large, but it's only like 8-9 megabytes. So
that would be great. Thank you.
Yeah, that way you can, now that you heard it and listen to the recording later, it'll make more sense.
Yeah, Greg, send it to me and we'll get it posted.
Okay,
and thank you, Greg, for being able to do this on such short notice.
Okay, no problem.
You've proven more reliable than Aviloa.
Yeah, I had this already prepared, but I had to update a lot of the. I had to update a lot of the slides, like these slides here. I had to update all this stuff here because this is kind of newer material. But I thank you for that, because I wouldn't have gotten to it if I didn't have to put this presentation together. That's kind of cool. And this stuff just came out. See this diagram here just came out online January 29th. And I was doing a search for the latest on Bennu, and I see this, and I'm like, oh my God, this is fantastic. So I was psyched.
Any other questions?
I have a question.
Yeah.
So, question or comment. So, I think you mentioned the two formation models for Ryugu, and they kind of similar, because while if it's an extinct comet, it would form also in outer solar system too, right? So
yeah.
So they both seems to suggest that the asteroid formed in outer solar system is just like where exactly formed, whether it's a Jupiter distance or even further out. And
right.
But I have also a comment about, I have a question about this distinct comet model. So that means also it might be a little bit hard to argue that, because you see this recent comet that just survived, Atlas comet survived perihelion, but then still disintegrated.
Yeah.
So
yeah, researchers agree that if you see this slide here, I didn't focus on this, but see
so that's the same comet.
Nitrogen and ammonia suggest that Bennu and even Ryugu was part of a larger asteroid. Ammonia ice is more stable further from a heat source like the sun. So ammonia-enriched ice melted inside the large parent body, creating a liquid environment inside the asteroid that could have formed these things. And then it was shattered and then reassembled closer to where it is now. See, so a lot of them agree that this had to form a lot further out, like 7 AU. See, and migrated closer. And then, and then the other researchers thought that it could be a comet, and it would be indistinguishable. They have what they call comet asteroid transition objects. See, so if an asteroid lost all of its, carbon dioxide, ammonia, all the gases, right, it would really be indistinguishable from an asteroid. So, because cometary nuclei do look exactly like Ryugu, and if you remember the Rosetta mission and some of the other missions to comets, so.
Yeah, I would just think that it would be a really large comet to begin with. Otherwise, it's just like
these are not that large asteroids. I mean, this is 0.3 miles and this is 0.76. So it's this one's double the size, but still it's small. I mean, you look at OSIRIS is the largest asteroid. I forget now how big it is, but I think Vesta's like 500 miles long. They're really huge, These have microgravity too compared to the larger asteroids. So NASA had to, make the spacecraft so they could orbit this successfully because there's very little gravity on these as opposed to larger asteroid.
Thank you.
Anybody else? Well, Greg, I want to thank you. First for giving the talk, second for giving it at the last minute.
Okay, no
really
problem.
appreciate you being able to jump in for us at the last minute. Really,
It's
truly appreciate it.
my pleasure.
Okay. Okay. Well, thanks everyone for coming, and special thanks to Greg for being our speaker tonight.
Okay.
Signing off.
Okay.